Hi guys, I'm live. I have my board again. I hope the video comes out. I hope you guys can see the board because I can't see the film that's filming because it's my camera flips it around. You can't. The writing is all reversed if I do it where I can actually see it being filmed. But if I do it this way, it's the writing is right, but I can't see what I'm doing. I can't see what you're seeing. So hopefully you can see this. So I noticed you guys liked the electronic theory thing yesterday, and Meta commented to me, people like to learn. So I just thought maybe once in a while I'll just draw it here and do some math or whatever to just to interest you guys if you guys care. So today I'm going to do a little trick I learned in that I didn't learn, but I made up. I thought of it myself in calculus. Well, some of it's just calculus material, but this little trick I'm going to show you is something I thought of. So in calculus, you have y equals e to the x. And that's a function such that y prime equals dy dx equals e to the x. So the derivative of the function is actually equal to the function itself. That's probably the only function I know of in math that's like that. It means however much you have, that's how much it's getting more. So like when you have very little, it's not getting much, but then you get more, it's getting more. And when you have a whole lot, you're getting even more than that. When you have zero or approaching having zero, you're actually getting nothing. But as you start to get more, and when you have approaching having infinity, you actually start approaching getting more at an infinite rate. That's what that means. Y equals e to the x, y prime, okay, y dx equals equals e to the x also. And so then I'm going to do another thing here. Now, there's such a thing as a natural logarithm. The natural logarithm of e to the x, if I can even write, natural logarithm of e to the x equals x. So the natural logarithm and the exponential function are inverse functions. One undoes the other, or you can put it another way: e to the log x equals x. The e to the logarithm of x is x, and the logarithm of e to the x is x. So these are inverse functions. Natural logarithm means base e logarithm. There's other bases, but e is the one such that derivative of e to the x equals e to the x. And e is I said once that e is I think I said it's a existential number, but actually it's a transcendental number. E is an irrational transcendental constant. There's no such thing as an existential constant. I had my terms wrong. Is 2.7. Well, let me write it so you can have more room. I have more room. E is equal to 2.718. Right. 281828. It goes on and on. It doesn't repeat 1828 again, but that's just how it starts. And then here's my little trick I learned. What is the derivative d, or what is d logarithm of x dx? In other words, what is the derivative of the logarithm, natural logarithm of x? We know the derivative of the x of e to the x is e to the x. What's the derivative of the logarithm of x dx? So what's the derivative of the logarithm function, basically? And there's lots of hard ways to do this, and here's a trick I discovered. I just did it on my own. I thought of this. Why not make x equals e to the y? Switch the x and the y, because you're going to be switching from. It made sense to do that because the logarithm function is the inverse function of the exponential function. So I thought, why not change the x and the y's? If x equals e to the y, then you have logarithm x equals, let's not do it like that. Then you have dx dy equals, dx dy equals e to the y, right? And then you have, yeah, I think that, how did I do this? Let me think. E with the y. Yeah, dx dy equals e to the y, because it's that was the derivative of the first derivative of the e to the y is e to the y. So then I did this. I inverted it. I went dy y dx equals 1 over e to the y. I did that. 1 over e to the y. 1 over e to the y. And then I had, but e, how did I do this? Whenever, I'm going to do this till I get it. It was x, 1 over e to the y. And then I did, dy dx equals, wait, no, I don't want to do that. I don't want to do that yet. I want to do this. Let me think. Let me think. X equals e to the y. Actually, I do want to, let me see. Dy dx equals 1 over e to the y. Okay, so I have that. Let's start with that. Dy dx equals 1 over e to the y. So dy dx equals 1 over e to the y. But I had that x equals e to the y. Okay, so I have that. But what is e to the y is x? Oh, that's my whole thing. That's the whole thing. So then I have dy dx equals 1 over x. And that is the derivative of logarithm of x. Because because remember I started with this. I started with x equals e to the y. That's what I started with. So therefore, if I have if I take the logarithm of both sides, logarithm of x equals y. I think I have that right. Like logarithm of x. Yeah, logarithm of x equals y. X equals e to the y. Logarithm of x equals e. X equals e to the y. Log x equals y. Right, e to the y. So 1 over e to the y. Oh yeah, I can make that backwards. I can go, okay, so I can go e to the y equals x. Then I can go, okay, so, and then I can go logarithm of e to the y is y, and that is equal to logarithm of x. See that? I made x equals e to the y, therefore e to the y equals x. Logarithm of both sides, y equals logarithm of x. And if y equals logarithm of x, dy dx equals 1 over x. So that's my equations right here. That last bit of trickery is all my own. That's why sometimes I have a hard time remembering what I did. It's not in the books, but that's my way of determining that the derivative of logarithm of x is 1 over x. Look at this piece of rock and roll.